I'll begin. Dear Father, we thank you for this day. We thank you for all your grace and mercy to us, Lord. Just pray that you'd help us to just do our best, Lord, today for your glory. In your name I pray, Lord Jesus. Amen. Okay, so I figured I should just start with the solution to the test to get that out of the way. Maybe you guys are not really the ones who need to see this as much, for the most part, but nevertheless, here we are. Okay, so we suppose that that's linearly independent, and you notice that I did not say that this is a set of column vectors or anything like that, right? So when you write a matrix of things involving x and y, you might be wrong. Now, if you're using the matrix to express a certain linear dependence between the vectors, that's possible. That still makes sense, right? But it worries me if you wrote a matrix here, because I don't readily see a matrix. Okay, anyway, so the point is, to prove that this is linearly independent, we suppose that the linear combination is 0, right? Rearranging, that gives me c1 plus c2x, c2 minus c1y is equal to 0. But linear independence of s then tells me that that coefficient and that coefficient are separately 0, which gives me two equations and two unknowns, which I can solve to get just the 0 solution, which then proves, of course, that t is in fact linearly independent. So, yeah, so, okay. So no, the rational numbers are not a real subspace of the reals, because if you multiply by pi, it takes you out of there, right? For example. I mean, sure, 0 is in the rational numbers, but it's not enough to have 0 in there, right? It has to be closed into the scalar multiplication. And the scalar multiplication of a real number, which is what we mean when we write this, is that our scalars are reals. Scalar multiplication by real number takes you out of the rational, so that's not in fact a subspace. This right here, now this is, I wish somebody had asked me about this during the test. I meant to put such that a comma b comma c are real numbers here, all right? So if you answered false on this question because you thought that a, b, and minus a were fixed but arbitrary constants, and that this was just a set containing one, containing one thing, if that's the reason that you put not a subspace, then I would be tending to give you back your points. But I think the reason most people got this wrong is something else. So, yeah. Anyway, that is missing. I meant to put such that a and b are real numbers. Okay. So with that clarification, then it's clear that this is really the span of x minus x cubed and x squared. So, okay. So anyway, any questions so far? No? Just interrupt me if there's something out of place here. This guy, well, that's a set containing 3 vectors that is not a subspace, right? If you multiply that by -1 or, add 2 of these, you're outside. There's so many different reasons this is not a subspace, right? The span of these things would be a subspace, right? But that's not the span of those things. So that was one of my unstated objectives on this test, is to try to get your class to better distinguish between S and span S. These are really different things, usually, right? So it's important to distinguish those two things. And there's a fuzziness in a lot of people's thinking, so they're not quite distinguishing those two things yet. Anyway, the set of invertible linear transformations forms a subspace. This is just not true, because if we take the identity map and we subtract it from itself, which we certainly could do in a subspace, we get the 0 map. And the 0 map, by the way, start with the 0 map. The 0 map's not invertible. Game over, right? So there's many, many different reasons that you could see here. Hey, this one, lots and lots and lots and lots of people got right. Woo-hoo. So there's the pretty standard calculate the coordinate vector and 2 by 2, R2. So that wasn't bad. Problem 3 wasn't bad. Problem 4, if I had to redo the test, I would put this one at the end. right? Because there's like 2 or 3 people in the class who got this right, right? Which I don't feel like that should be the case, but it's just, you know, yeah. Maybe if I ask this kind of question again on the final, people will get it. I don't know. We shall see. So the question here is, what can I put in this third spot in order to get a basis for P2, right? Now, I gave some partial credit if you just had at least enough insight to write that as an arbitrary vector. That's a good starting point, to write ax squared plus bx plus c. Then what do you do with that? There's various approaches. My approach would be to look at the corresponding coordinate vectors with respect to the standard, well, the usual basis for P2, namely the monomial basis. I called it gamma here. So the coordinate vectors of this, this, and this are that, that, and that with respect to the gamma basis. And in order to get linear independence of this set of 3 column vectors of length 3, I just need the determinant of that corresponding matrix to be non-zero, which gives me this condition a plus b minus c not equal to 0. So basically, I can take any f of x of this form with that condition, and that will make beta into a basis. You have many choices. Now, there are, of course, other ways you could attack that problem. Like, that determinant idea is helpful, but it's not necessary. You could have just worked out the algebra on A, B, C to see what it would have taken to make the vector, the other vector, and then ax squared plus bx plus c linearly independent, right? That would have given you I think it would have given you 3 equations. Excuse me. Well, anyway, if you'd sorted out the algebra there, you should have come to the same condition. And I think one person did. Anyway, this one, pretty standard question. We use this all the time, but, you know, one of the things you should pick up in linear is that when we use something all the time, that doesn't mean that you can't ignore the proof. I mean, you should also be able to prove it, right? So we hold ourselves to that standard in here. Anyway, so T of linear transformation is supposed to prove that the kernel being 0 implies T is injective. You can see from all my whiteout that I couldn't stay on task when I was writing my solution. I kept proving the other direction or something stupid. But I finally chopped my solution down to just what I need. So linear, suppose the kernel is 0. Take x and y and v, for which T of x is equal to T of y. That would mean that T of x minus T of y is 0. And consequently, T of x minus y being 0. Consequently, x minus y is in the kernel of T. But the kernel of T is 0, which means that x minus y is equal to 0, which then tells you x is equal to y, which is what I needed to do in order to prove that T is injective. Right? So that's that. Many more people got problem 5 right than problem 4, right? So like, problem 5 was, some people were successful. Problem 6, I think a lot of people got this. Not getting part B of this suggests to me that you haven't been very serious about studying for this course, frankly, because we have done a lot of these at this point. Not this exact one, but problems like it, right, where we have a linear transformation from an abstract vector space to another abstract vector space, and we find the matrix of it, right? Often we've worked more complicated things where the basis in the domain and the basis in the codomain are different, but it should be the same thought process, right? Now, for part A, a lot of people got this right. I was very happy. So, you know, we have to look at a linear combination, apply the definition, matrix arithmetic, and then the definition again. So that gives me the homogeneity and the additivity for T, which shows that T is linear. The next part, I just look at the formula to start as my starting point. I need to figure out what's the formula for T, and so that is right here, just feeding it an arbitrary matrix A, B, C, D, right? And then, so I sort through that. Basically need to fill in this blank. I need something times A, B, C, D to give me this A plus 3B, 2A plus 4B, C plus 3D, 2C plus 4D, because the coordinate, you know, because of the beta coordinate system went this, like E11, E12, E21, E22. That's why I have this here. Anyway, that gives me this matrix. 1, 3, 2, 4, zeros, and then 1, 3, 2, 4 in the other block, which, by the way, is this. B transpose 0, 0, B transpose. So. As you're studying for the final and stuff later, a fun problem to work is just like this one, but to see what happens if instead of making the formula AB, what happens if you change the formula to BA? How does the matrix look different? It's kind of interesting. It may be even an example in the notes. I can't remember. It'll change it considerably. All right. So here, problem 7. Is this linear transformation an isomorphism? All right. So here, there are a lot of things you can observe. First of all, we've already proved that this T is linear in the previous problem, right? So that's settled. It is linear. And you look at it, the domain and the codomain are the same vector space. So certainly we have the equivalent, the following our equivalent theorem as regards to the injectivity versus surjectivity, right? If it's injective, it's automatically surjective and vice versa. So really, I could either prove the kernel is 0, or I could prove it's onto, right? Either one of those would suffice to prove it's an isomorphism, right? But just to be, make sure everybody understands how to do things, I put everything here. So number 1, to prove it's onto, if you just look at x and R2 by 2, if you map to that by x times b inverse, that's this, which is that, so T is onto. So there you go. On the other hand, to prove the kernel 0, suppose that A is in the kernel T, that means AB is equal to 0. Multiplying by B inverse gives us this, which gives us that. Well, the kernel 0. Hence, T is 1 to 1. So however you slice it, T is a linear bijection. That is to say it's an isomorphism. In fact, this is what's called an automorphism because it's an isomorphism of the vector space R2 by 2 in itself. Any questions here? No? All right. A lot of people nailed this. If you didn't get this right, there is a serious gap in your understanding. Because at this stage in the game, we should all be able to calculate the basis for the null space. We have done this, right? This has happened. This was on the I think I didn't call it a basis on the last test, I don't think, right? But if you look at it, in some sense, this was even on the first test. The kind of calculation here, right? But anyway, so to find the basis for the null space, we row reduce, at least I do. And once I get the reduced row echelon form, I can read off the solution in terms of the pivot variables being dependent on the non-pivot variables, in this case, x3, x4, x5, which gives me this equation and that equation, plug it into the arbitrary vector, pull out my parameters, in this case, x3, x4, x5. It leaves me these 3 vectors for the basis for the null space of A, which, again, a lot of you got. Problem 9, I think about 2 people get this, maybe. I don't remember. Not many. So for A as in the previous problem, find an isomorphism from the null space of A to the symmetric 2 by 2 real matrices. So the point here, I mean, the one thing you should take away from everything else about isomorphism is that basically to judge whether or not 2 vector spaces are isomorphic, it just is to ask the question, supposing they're both over the same field of scalars, right? Do they have the same dimension? If they have the same dimension, they're isomorphic. How do you construct the isomorphism? Well, there's a few different ways, but one of the ways I told you guys is that you just map the basis to the other basis, right? Since you've got 3 things in one, you've got 3 things in the other, any map of those 3 things to the other 3 things will do. That means there's lots of different choices for isomorphism, right? Because you could map the first to the first, and the second to the second, and the third to the third, or you could map the first to the third, the second to the second. I mean, there's lots of permutations of the one basis to the other. But here's what I did. I said, okay, well, I'm going to map this linear combination, right? Here's my arbitrary vector in the null space, and I'm just going to map it to this 2 by 2 symmetric matrix. So, yeah. But anyway, if I'd been smarter, I would have given these things labels back here so I wouldn't have to keep writing them. You know, this is like the third time I've written these stupid vectors. It's like, why am I writing these so many times? Poor planning on my part. This problem was your guys' fault. So like, I said something like, oh yeah, we'd like to have that problem. I was like, okay, I'll put it on there. So I forget who, someone in here. It's all your fault that this problem was on the test. And again, I think about 5 people who were kind of in the hunt. There were others who were, further away. But this is basically what I was looking for. I said include a diagram which motivates the coordinate change formula. The diagram does not prove the coordinate change formula, right? But if you look at this diagram, you can see why left multiplication by the A matrix is the same as left multiplication by the A bar matrix if we also adjoin to that, you know, this mapping and then that mapping. So that's where I get this equality. L of A bar, well, I'm sorry, the other way around. This map, this journey is the same as this and, how to say this? I still haven't said it right. Going from here to here is the same as going from here to here to here to here to here, is the idea. And so that's where this formula came from. The green path is that formula right here. Now, why is this, why is this equal to that? It's because if you could, you could solve both of these for t and get the connection. I'm sorry, excuse me. If you look at this, that's the identity map. That's the identity map. So all I've done is insert the identity map into the definition of LA bar. So this is LA bar by definition. So if I insert the identity map like this, and if I insert the identity map like that, then we just have straight equality of these maps, right? So again, the picture motivates writing that equality, but really the picture is not the proof. It's just a guide. The proof is just that this is a tautology, essentially. Right? I haven't really properly proved it. If I was going to try to more properly prove it, I should really write another line that says insert the identity here, insert the identity there. This would be the identity on, I think that would be the identity on FM, and over here I'd be inserting the identity on FN, right? So these are mappings that go from, they're opposite. So this would be the identity on, goodness gracious. Well, let me stop talking, maybe while I'm ahead. So anyway, however you come to the understanding, this is the relation between the L sub A and the L sub A bar. And then the standard matrix of LA bar is A bar. The standard matrix of L sub A is the T beta bar gamma. And then this is the standard matrix of that. I'm sorry, it's the standard matrix of that. And this is the standard matrix of that. Right? And why is this the product of 3 standard matrices? It's because if you look at this map and that map and that map, they're all mappings on column vectors, right? They're mappings from column vectors to column vectors of either m or n size. And so we have this result for standard matrices of a composition of linear maps, is that if we have a composition of S1, S2, S3, where those are mappings on column vectors, then the standard matrix of S1 composed with S2 composed with S3 is standard matrix of S1 times the standard matrix of S2 times the standard matrix of S3. Again, that's something we proved in the first part of the course. Right? Did we? Am I wrong? Did we talk about linear transformations in test 1? No. So it's something we proved since last test. I'm sorry. I sometimes forget where we learn things. Okay. Again, my apologies here. I should have written in the statement of the problem that we're linearly extending. You know, this is the value of t on the basis, and then we're linearly extending to the whole vector space. All right? When I say that, you don't have to prove that it's a linear transformation. It is by construction a linear transformation. So I was a little bit sad that I saw a lot of you trying to prove it was a linear transformation after I told you on the board, of course, that T was defined by linearly extending off the basis. The point of that linear extension theorem was that in so defining T, we don't have to prove linearity because it's given to us by the very construction. And you had a homework which was exploring why that was uniquely the case to define the function as such. Okay, anyway, getting past that, this is a linear transformation from V to V, right? So again, to prove it's an isomorphism, it suffices to either prove the kernel 0 or to prove it's onto, because it's mapping from V to V again, right? So to prove the kernel 0, I would just look at T of x being 0. You notice that x would be a linear combination of the basis. Like the common mistake here, people were just working with the basis, and while that actually would suffice, you should explain why. So anyway, so if that T is 0, that gives us this as 0. But by linear independence of the f1, f2 to fn, I get that, xj times j squared is 0 for each j, right? But j squared, of course, is non-zero because it's 1, or it's 2, it's 9, it's 16, it's 25, whatever. Those are non-zero numbers. So that implies that the coefficient x sub j is 0. But all of the coefficients x sub j being 0 implies that x itself is 0, which is to say that the kernel of T is just 0, right? Consequently, it's 1 to 1, but it's also onto because, again, this is a linear mapping from V to V. It's an endomorphism. So T is both 1 to 1 onto, and so it's an isomorphism of V. I have the proof of onto down here if you wanted to go that direction. If you pick y in V, then y is mapped to by this 1 over j squared, yj fj sum over. So when you feed this to T, it multiplies by j squared and spits back out y again, which proves onto. Anyway. And probably problem 12, nobody got. Some people were, anyway, nobody got. I'm trying to think what was the least wrong thing written here. People wrote some things which were true. They were just like, yep, but keep going, Anyway, here it is. So about 5 people told me it was a trace. Fantastic. I'm actually very happy about that. That you guys remembered that's what that's called and had an understanding that's what the trace is. That's actually good. Not everybody did that, right? But yes, in fact, that's the trace, which is one of the most famous examples of a linear functional, or a dual vector, if you like. We had this result that any dual vector is the sum over the dual vector acting on the given basis times the corresponding dual basis. So when I derived this in class, this looked like alpha of e lower I times e upper I, right? But in the current context, it's got a double index because we label the basis with a row column index. That's just more convenient for a matrix basis, right? I don't know if you thought about this or not, but that ij is playing the same role that just I or just j does in our more abstract discussions of dual bases. That could have been a stopping point for you, right? If you couldn't get past that mental block, if you couldn't see past the notational idea, if you didn't have a conceptual idea of this result and what it means in this context, in this notation, I could see how that would have stopped you, which is why I put this at the end of the test. I had that much sense, at least. Not to make this problem 1, But anyway, this is a generic result. So, but also this indicates that, in fact, this is the coordinate, this is the component of the coordinate vector of alpha with respect to the e upper ij basis. So to write down the coordinate vector with respect to the dual basis, I just write this down according to the lexicographic ordering. But the trace of these matrices is usually 0, or it's possibly 1. It's only 1 on the diagonal basis, like the E11, the E22, the E33, ENN. So what you get is a coordinate vector which has got like 1 in the first spot, and then you go n. This is like the n plus 1th spot, I think, and then the 2n plus 1th spot. Is that right? I can't count. But every n, you've got a 1 right until the end. So that's what the coordinate vector looks like. Sorry, it's not a very exciting question. I'm sure if I'd asked something about annihilators, there's any number of you who probably would have done better. But I think I needed to ask another coordinate vector question here somewhere so it fit the bill. And anyway, any questions? Man, I should have brought something to drink today. No? So you guys have come to terms with whatever happened on the test for you personally, and you know how to fix it? I will ask this. Is there anything that I didn't test on in this test that you were disappointed that I didn't test on? That's like being asked to testify against myself. I refuse to answer that question. Yeah. All right, well, anyway, let's go on then. Oh. Let me steal something from my notes, because I neglected to bring my notes with me. I'm sorry, guys. Let's see here. A equals to 3131A. All right. And what's my other example? Zero, zero, minus 4, 2, 4, 2, and 2, 0, 6, right? So I think in the next homework, I've assigned you a bunch of calculate the eigenvector problems, right? Have you looked? Let's look together. What mission are we on? 7. Wow. Already in mission 7. Time flies when we're having fun, huh? Let's see here. So, to start with, we have some more fun things. So it's just probably useful for us to go problem by problem and give you some short hints, right? This one, you got a two-dimensional subspace of R4, another two-dimensional subspace of R4. You're supposed to show that the direct sum of W1 and W2 is R4. How would you do that? Right. Intersection 0. That would be but direct by the definition to show that their sum is R4 and that the intersection 0. Very good. That is one way. Another way we could attack this, remember our theorem about equivalence of internal direct sums for a given subspace? One of the theorems we had was if we could take the basis for W1 and the basis for W2, and if we can string them together and get a basis for the whole space, then what? Then that proves it's an internal direct sum. That was one of our equivalent conditions. That might be the laziest way to do this one, because what's the basis for W1? You're looking at it, right? What's the basis for W2? Again, looking at it. So what does this question really boil down to? The question is, if you put these 4 vectors together, do you get a basis for R4? Because then we can use the equivalence theorem. You know which theorem I'm talking about? The theorem I am referencing is can't believe you asked me to prove that. Anyway, sorry. I'll get over it eventually. This theorem, right? So the definition is what you were saying, Bethany, which is, oh, it's not even the definition. It's kind of, sort of, it's 2, right? I mean, it's the preamble married with 2 in the case of 2 things, which is not, I mean, that's good. It's the right way to approach a lot of problems, especially when we don't have the basis given for the 2 subspaces. That's the right way to do it. This one, just this particular problem, though, because I have beta 1 and beta 2 in hand, 4 is a convenient, way to check if it's the direct sum. No. Well, I think it would follow, right? If, I mean, what's the basis for W1 plus W2? It can be selected from the union of the basis for W1 and the basis for W2, generally. So if the union of the basis for W1 and W2 gives me all of R4, then that proves that W1 plus W2 is R4. I don't want to talk you out of a more careful solution, though. So what I'm saying only makes sense as much as I reference the appropriate set of theorems. But yeah. Problem 110. V is the direct sum of W1 and W2. Does it follow that the annihilator of W1, direct sum of the annihilator of W2, is equal to V dual? Ooh. I don't know. I'm going to let you guys think about that one. Here, I believe it's possible that the beta 1 and the beta 2 are actually what? This is interesting if the span of beta 1 and the span of beta 2 are invariant subspaces of T, right? If they are invariant subspaces, then when we look at, well, first of all, if they're not, part A is really hard. So if they are invariant subspaces, that means we can define these maps, right? And then the neat thing is that we should be able to see that the matrix with respect to the concatenated basis is this like block diagonal structure, yeah? All right, let me go on here. Uh-oh. Phew, I almost worked that. See, this is almost my example 4, right? There's something very similar to this problem in example. They're not this in example 4 are not exactly the same, but I don't know, they're in the same ballpark. Let's see here. Suppose V is a finite dimensional vector space over a field, that the sum of W1 and W2 is V, and the dimension of W1 plus the dimension of W2 is the dimension of V. Prove this. Now here, I definitely want to take Bethany's approach and use what she said about 2 subspaces. They're the direct sum if the sum is V and if the intersection is 0, right? So you're given that the sum of W1 and W2 is V here. All you need to do is figure out a way to prove that the intersection is 0. I would point out there are theorems in the notes that you could use that would make this a 2-line problem. I can't say any more, otherwise I'll solve it. Here I'm introducing you to an idea, which is that we can take a polynomial and we can plug in the matrix and get a corresponding matrix. All right? We can also do the same thing with like taking a linear transformation, because if you think about a linear transformation from V to V in endomorphism, you can compose it with itself. Like if T goes from V to V, then T squared goes from V to V to V again. So the square, the cube, so forth. Powers of an endomorphism make sense. And so you can either plug in, likewise, powers of a square matrix make sense, right? So if A is a square matrix, I can plug it into the polynomial, and that's a reasonable thing to do. And what's the point of this problem is to see that if V is an eigenvector of A, right, then it's also an eigenvector of this matrix. Here, I'll show you a special example of this. If I had f of x equals to x squared plus 2x minus 3, and if I had that AV was equal to, lambda V, so what's f of A? a squared plus 2a minus 3 times the identity matrix. So I take f of a, I multiply it by v, what do I get? I get AAV plus 2AV minus 3IV, right? What's AV? That's lambda V, right? And if we pull the lambda out, we get lambda squared V here. And then factor the V out, we got lambda squared plus 2 lambda minus 3 acting on V. This is exactly f of lambda. So that's kind of a neat thing. If we have an eigenvector for a matrix, it also becomes an eigenvector for any polynomial of the matrix. But the new eigenvalue is no longer just the lambda that you started with. It's whatever happens to lambda when you feed it to the polynomial in question. So for a simple example, if I had an eigenvector of A, had eigenvalue 3, and then I ask, is that same vector an eigenvector of A squared, right? Well, yes, it is, and it's going to have eigenvalue 9. Here, let me just turn on the lights here. So you guys are not following me yet, I don't think. What does it mean for A to be an eigenvector with eigenvalue 3? I mean, V, rather. It means AV is 3V, right? This is what it means for A to have eigenvector V with eigenvalue 3. Subject to what condition? There's a string attached. I need to know something about V. What do I need? Very good, non-zero, yeah. So if I take A squared times V, well, that's AAV, right? Which is A times 3V. Pull the 3 out, that's 3AV. That's 3 times 3 times V, also known as 9V. So really, first you should understand this, and not just for the second power, but you can prove that this works for any power, right? So, did I do this in class? I didn't. I feel like I didn't. Did I do this? I'm sorry, guys. I've forgotten if I actually did this. I did something like this in class. I don't know if I exactly did this. I think I did something more complicated as it relates to the diagonalization of a matrix, right? So this is kind of the nuts and bolts of that in some regard. Anyway, right, so this problem is actually not as bad as you might first think it is. Problem 115. What does it mean for the k minus 1th power of a matrix to be non-zero? I mean, that means that there's at least some column in it which is non-zero, right? So you probably should think about that column as it relates to the kth power being 0. Maybe that's... Well, anyway, I feel like that was part of the solution here. I'm actually a little rusty on what exactly I did to solve this. As I recall, this required some amount of thinking. Let's see here. I can see a contradiction solution for 115. Suppose you had a vector, an eigenvector with eigenvalue not equal to 0, right? By the discussion we're just having, what would a to the k acting on that vector B? Lambda to the kv, where lambda k is non-zero, right? So that would say that there exists a vector, a non-zero vector v, that when you multiply by a to the k, you get a non-zero result, right? You should be able to prove that contradicts the fact that a to the k is 0, right? Because if a to the k is 0, that means that all of the entries of a to the k are 0. And that stands at odds with what I just rattled off. Oh, and then finally, this is what I actually want to talk to you guys about mostly today. Here's some specific numerical matrices. Find the eigenvalues, find the eigenvectors, right? So I have given you a list of specific numerical problems that I think should sort of alert you to the different kinds of cases that are out there for 2x2 and 3x3 matrices. But there's a few of these here, right? And for each one of these, I ask about eigenvalues, eigenvectors. Is it diagonalizable as a real matrix? Is it diagonalizable as a complex matrix? Find the real Jordan form associated with A. I have not defined the real Jordan form just yet. Next class, I will start talking about the Jordan form, but I still need to do a little bit more legwork on linear independence of eigenvectors, right? Okay. Whee! Oh, wedge products again. Woohoo! Let's see here. And then what? Oh, and then these are my, at this point, from this point on out, I have put questions I didn't collect, but I think are interesting. So, yeah. Okay, so I will, okay, so what I want to show you guys, the reason I haven't put this away yet, is partly because I wanted to alert you to the fact that there is a wonderful website to check your work on the eigenvector problem, okay? So, I think I have it linked. So you guys have, right under that, eigenvector calculator. I prefer the old version of this calculator personally. And so here it is. This is a matrix set -7509. Calculate the eigenvalues and eigenvectors. So it gives you the characteristic polynomial, which in this case is x squared plus 16x plus 63. It tells you that the real eigenvalues are -9 and -7. And it tells you the eigenvector corresponding to each eigenvalue. So this is very nice way to check our work here, right? I would encourage you probably need to work these by hand for the most part, because you guys need practice, right? So, but I don't object. I mean, if you don't feel like you need the practice and you just want to get through it and you want to use this website to do the numerical stuff, that's also fine, right? But beware that that's a sword you can cut yourself with, so to speak. I mean, if you're not careful, if you do too much of that, then you won't be prepared. Yeah. Okay, anyway. So, like, for example, we could try this one, 3, 1, right? And it would tell me the characteristic polynomial. Now, so there's something to be aware of. His characteristic polynomial is minus mine. I mean, his is determinant of xi minus a, whereas mine is the determinant of a minus xi. Other way around, yeah, a minus xi. So I think you have to multiply by a minus sign to get his characteristic. Well, it depends on the size of the matrix, but so yeah. And it'll do complex ones too. Like here's a matrix with complex eigenvalues. Right. So, oh, you can't see it, but it was just 3 minus 1, 3, 1. And we get complex eigenvalues of 2 plus or minus the square root of 2i in this case. You can tell that's square root of 2, right? Square root of 2. And here are the complex eigenvectors. Here's the thing to notice about those. You notice the relation between this vector and that vector? It's like the same pattern, right? Except what? the I term has been flipped with a minus, just like the eigenvalues come in a conjugate pair as well. This is something we'll see for real matrices. The complex eigenvalues come in complex conjugate pairs, and likewise the eigenvectors. All right, anyway. Put this away. So I just wanted to alert you to that website because it will save you a lot of time and aggravation as you're working on those numerical problems eventually. All right, so let me just go through how we find the eigenvectors and eigenvalues of this matrix, all right, step by step. I mean, if you want, I can make up a different matrix, but I think it doesn't really matter that this is the one that's in the notes as well, because the steps are the same. So step number one is to find the eigenvalues. How do you find the eigenvalues? We need to look, calculate the determinant of a minus lambda I, and set that equal to 0, try to solve it, right? Let's see here. So that's the determinant of 3 minus lambda, 1, 3, 1 minus lambda. Which is what? That's 3 minus lambda, 1 minus lambda, minus 3. And here's a trick. I don't know about you, but I much prefer to multiply these, right? Isn't that nicer to look at it that way? So I almost always do that. I usually will go straight from here to there when I'm calculating, honestly, guys. I personally find it's convenient. Anyway, so this gives me lambda squared minus 4 lambda plus 3 minus 3. Aha! So that's lambda times lambda minus 4. Therefore, lambda 1 is 0, and lambda 2 is 4. There you go. Them's your eigenvalues, 0 and 4. So what are the eigenvectors then? So let's see here. For lambda 1 equal to 0, we're trying to solve a minus 0 times I times some vector, let's say v1, equal to 0, right? We're trying to find a v1 to, like I said, all of a sudden I'm using vectors. What's wrong with me? Vector symbol. What is this, calculus 3? Anyway, so of course that's just really what? We're really just looking for, this means that v1 is what? In the null space of A, right? So how do you, I mean, that's what? This is 3, 1, 3, 1. So that's, 3, 1, 0, 0. I don't know. Do you really even need to write that? You should be able to see here that if v1 is uv, right, then we need 3 times u plus v equal to 0, right? That's the condition that we must have on v1 in order that it be in the null space, that it be in the 0 eigenspace. So that gives me, I guess if I do the way things we usually do, I'd say u is minus v over 3, right? And so therefore, v1 is minus v over 3, comma v, which is v times minus 1/3, comma 1. That's what an arbitrary eigenvector with eigenvalue 0 looks like, right? So, but to make things prettier, I would say, therefore, the eigenspace 1 is just the span of what? Give me, if we hate fractions, right? So what would be a better choice here? How about minus 1 comma what? What's that? Oh, 3. Okay, yeah. And so what you're looking at in the curly brackets, that is a basis for the 0 eigenspace, right? And then we have what other? 4, right? So lambda 2 equals to 4. I'm trying to solve a minus 4i, right? And let me just get straight to the point. Times a vector uv equal to 0, 0, right? You notice that inventing the symbol v1 didn't really do much for us in the previous step, right? So if I'm actually interested in the specific details here, so let's see here, a minus 4i is what? It's minus 1, 1, 3, minus 3. So I'm trying to find a basis for the solution set here to this homogeneous equation. You can, I mean, do I need to do row reductions here? I don't think I do. I think it's manifest from this point already that these two equations are the same equation, right? So it suffices, we need what? Minus u plus v equal to 0. So my vector u comma v is really just what? V comma v, if you like. So E2 would be the span of 1, 1. So finding eigenvectors is just doing a null space basis calculation, right? But it's not the null space of the matrix itself usually. Usually it's the null space of an associated matrix, like A minus lambda times the identity. Now, in the first case, it actually was straight up the null space because lambda equal to 0 is an eigenvalue, right? How many eigenvalues can we have for a matrix? What? At most n, yeah. And that's true whatever field we're working over, because over any field, if you have a 0 to the characteristic polynomial, that generates a factor of x minus that root, right? So if you had more than n roots to an nth order polynomial, that'd be very troubling, because when you apply the factor theorem repeatedly, you'd be able to generate the polynomial being higher than order n from those more than n roots, right? So it's not even a real or complex thing. It is, of course, the case in the complex case that we will have n complex solutions, possibly repeated. In the real case, we might not have all the eigenvectors, right? But we will have corresponding complex eigenvalues for the real case. All right, anyway. But technically speaking, a complex eigenvalue is not a real eigenvalue in the technical sense. Now this one here, yep.
So the eigenspace is all the vectors that have that eigenvalue? Is that what that is? Or
Yeah. Right. It's all the vectors that have that eigenvalue. That's right.
And then over on
And the 0 vector.
Okay. Why is it that you choose to choose it? Like, why does that tell you the eigenvalue?
Well, fair enough. So we're looking for a solution to a minus lambda I times v equals to 0 for v not equal to 0, right? But you know that a minus lambda I times 0 is equal to 0, right? Thus, the null space of a minus lambda I is not equal to 0, which implies that A minus lambda I inverse does not exist, right? So since we're working over a field, to say that the matrix has no inverse is just to say that its determinant is 0. And so it stands to reason then that looking at this characteristic equation, which I just boxed, that is a necessary condition, right? That's a necessary condition if we're going to have a lambda and a non-zero vector v that solves that equation, a minus lambda iv equal to 0. Right? So that's why I'm looking at the characteristic equation, because it has to. But this chain of thought also reverses. So if this is equal to 0, then the inverse does not exist, which means that the matrix A minus lambda I has more than just the 0 solution to the homogeneous problem, as we discussed. And that more than just 0 solution to the homogeneous problem for A minus lambda I is an eigenvector with eigenvalue lambda. So it all goes back to that discussion we had earlier in the course about the relation between what it means for a matrix to be non-invertible, right? That there exists a non-zero solution to the homogeneous problem, right? That the determinant is 0. These are equivalent conditions. And there are equivalent conditions here which tell us what the eigenvalues possibly can be. So that's why I look at it. Does that make sense?
That part makes sense.
What doesn't make sense? You're choosing your words. Sneaky. Something feels off, but you're not sure what it is yet, is what you're telling me. I can respect that. No? Yes? Okay. Let's do this one. Let's see, maybe it helps. So what's the determinant of A minus lambda I here? Oh, it's horrible. Because it's 3 by 3, yes. Is it just the matrix, the subtracting lambda times identity matrix? That's not it. That you get.
I mean, just like, why do you see the eigenvalues is what I'm saying.
Again, to say that there's an eigenvalue is to say that there is a non-zero vector such that, AV equals to lambda v. That is equivalent to this. But again, that means that this matrix, if you want to call it B, call this thing B, right? It says that matrix B is not invertible, which means that its determinant is 0. But that determinant involves the lambda in a kind of surprising polynomial way. Yeah. Oh. Why did I do this to myself? I mean, so this kind of thing, guys, you just got to be careful. I mean, that's like the thing I say right before I make a mistake, right? Ooh, yay. Check it out, yo. Factoring by grouping is huge in these problems, if you can see it, because the main trouble with a cubic is finding the one thing to factor out. Once you have that, it's a thing times the quadratic, which we own, right? It's the first factor of the cubic, which is a pain. But I just found it. It's lambda minus 4, and then we've got minus lambda times lambda minus 6. Looks like minus 8.